In this lecture, we're going to talk about polynomial inequalities. And there's a pretty nice procedure for figuring out the solution sets for these things. And let me show you with just a bunch of examples. So let's graph the solution set for the following, and then we'll write out the interval notation and algebraic version of the solution set. So we're going to get three different ways to write out the solution set. So the procedure is, okay, so whenever you're presented something like this, step one, you're going to write out the factorization of it. So factor and compare to 0. So what I mean by that is first bring everything to one side of the equation. So you see how here everything is already on one side and you're comparing it to 0. So we're going to factor what's on the left here. Okay, and then what you're going to do is find the zeros. Find the zeros as if this was equality. Okay, and then step 3, you're going to plot those zeros. Plot the zeros on the number line as an open circle if you're dealing with less than, or if you're dealing with strict greater than. And then you're going to use a filled in circle if it's less than or equal to, or greater than or equal to. And you'll do that for all of the zeros that are involved. Now, what you're going to have done is you're going to have divided up the real number line into regions split up by these points that you're plotting. And then what you're going to do is step 4. This procedure will make more sense as I go through it with this example here. Step 4, sorry, let me just move this up a little. So step 4, you will pick a value in each of the intervals and test if the inequality is valid or not. And you will include the regions where you get a valid the inequality is valid. And that will fill in the real line with the valid regions and the unvalid regions, and that'll determine the solution set for us. So let's do that with this example right here. So we have already compared the left-hand side here to 0, and so we're going to start by just factoring, right? So step 1, factor and compare to 0. Okay, so what is this factorization? So we are going to have x, and we need the product to be minus 15, but the sum to be positive 2. So that looks like it should be x plus 5, x minus 3, less than 0. Okay, so we did step 1, we factored, and then we are going to find the roots as if this inequality was equality. So the roots are x plus 5 equals 0. Like as if this was equal to 0, then you'd have x plus 5 equal to 0 or x minus 3 equal to 0. Even though that these two, since it's a strict inequality, are not going to satisfy it, we're still going to find these roots. So we have x is negative 5, and we have x is positive 3, adding 3 to both sides here and adding negative 5 to both sides here. Okay, so we have found the zeros as if the inequality was equality, and now we will plot the zeros on the number line. So we're going to draw a number line now. Okay, and it says to plot these zeros with either a filled-in circle or an open circle. Okay, now I'm going to switch to a different color here just to make that a little clear. So -5, and this is a strict less than. We're not allowing equality here, so these are not actually going to solve this inequality, right? So I'm going to put in an open circle at -5, and I'm going to put an open circle at 3. Okay, so if I were to plug these in, it's easier to plug things into the factored form, right? If I plugged in -5, this would be 0, and so this would be 0. And 0 is not strictly less than 0. It's because they're equal, right? So that's why these are not going to be included in the solution set. So now on to step 4. So we're going to pick a value in each of the intervals. So what do I mean by that? Well, notice that we plotted the zeros, and we've broken up the number line into these 3 pieces. We have a piece over here. We have a piece in the middle in between the two, and we have a piece over here. So what we're going to do is just pick a test value. All right, so test values. We're going to pick over here just something that's less than -5. So how about x is equal to -6? And here, what's in between there that's simple to plug in? Well, x equals 0. What's something bigger than 3? X equals 4. But again, these are test values. You can pick anything that you want as long as they're within these regions. Okay, and then now what you're going to do is you're going to plug in these test values up here and see if we get a valid inequality. Now, keep in mind, I don't actually need to simplify it fully because all I'm really determining is the sign here. Since I'm comparing it to 0, all I got to do is just show that the left-hand side, if it's negative, then it'll be less than 0 and it'll be valid. If it's 0 or positive, then I'm getting something that's not valid. So let me show you what I mean by that. So plug in x equals -6 into this factored form. What do I get? You'll get -6 plus 5, -6 minus 3. Okay, now I don't actually need to determine what these things are, even though I could do that really quick, right? This is -1, this is -9, and you could figure out that that's what? That's +9, so this is not going to be valid. However, what you could just do is pay attention to the sign. See that this is negative? -6 plus 5 is negative. -6 minus 3 is negative. And what's a negative times a negative? Well, that's a positive. Sorry, this froze for a second there. That's a positive. And that means that if you're getting a positive on the left, then that's not less than 0. So we're not going to include this whole region here. What happens if I plug in 0? If I plug in 0 here, then I get, what do I get here? You could do this. 0 plus 5, that's a positive. 0 minus 3 is a negative. So this is a negative. And negative is less than 0. So what that means is we're going to include this whole region. Right? This is, the inequality is valid here, right? If I plugged in 0, 0 plus 5 is positive, 0 minus 3 is negative, negative times positive is negative, and that means I'm getting a negative number here. So everything in there is going to be a negative. What if I plug in 4? If I plug in 4, then I have 4 plus 5 is a positive, 4 minus 3 is a positive, and a positive times a positive is a positive, and that is not less than 0. That's not a negative, right? So we're not going to include that. So this is our solution, right? So that's the graphical solution. How do I write that as an interval? Well, I'm not including this, so that's -5 using a parenthesis up to 3 and another parenthesis. And then I also want the algebraic version of the solution. Well, I'm just saying x has to be between these two, right? So that would be between -5 and 3, just like that. Continuing on to our next example, let's follow the same procedure. So, well, okay, you know what? I could add a step 0 to that procedure. Notice that all these coefficients have a common factor of 2. Now, I could just factor this normally, but we all know that it's a lot easier to deal with things if you can, reduce those coefficients. So if I actually divide everything by 2, look at this. So if I divide everything by 2, that's a positive. So that's not going to flip that inequality, right? So divide everything by 2, and I'm going to get something a little easier to work with. So this would be x squared plus 4x minus 12 greater than 0. 0 over 2 is 0. And then I can just proceed with this, which is going to be a little bit simpler to work with. Okay, so what's the next step? We're comparing this to 0, so we're going to factor the left side. So this is x. We want the product to be minus 12 and the sum to be 4. So that looks like it should be plus 6 minus 2. And then now let's find the roots of that. Well, the roots would be x plus 6 is 0, so that's x is equal to negative 6. That's one of the roots. And x is equal to 2, right? If this is equal to 0, then you'd have to add 2 and you'd get x equals 2. Okay, so now let's plot that on the real number line. And we're dealing with a strict inequality here. So these are going to be filled in circles. Let me switch to a different color again. Okay, so then this would be negative 6, open circle, to 2, open circle. Okay, and now let's pick some test values. So what are some good test values? We could pick x is negative 7, x is 0, x is 3. Those seem pretty good to me. So let's plug in negative 7 into the factored form. So if I plug in negative 7 right here, you will get negative 7 plus 6 is a negative. Negative 7 minus 2 is a negative 9, so that's a negative. Negative times negative is positive, and that's greater than 0, right? So that will be included in our solution. Okay, that's good, right? We're looking for positive. If I plug in 0, 0 plus 6 is positive. 0 minus 2 is negative. Plus times minus is minus. So that's not going to be included. We're not going to include that portion of the region. Then x equals 3. 3 plus 6 is a positive. Again, notice the nice thing about this. Everything is factored, right? So I don't actually care what the values are, which can just save you a little bit of time. Of course, you could figure out the values, plugging these test values into the original thing, but you don't need to do that. We just need to figure out the sign because we're comparing it to 0. So that means we're either dealing with a negative, a positive, or 0 itself, but the only zeros are going to be at these points here. So we know that in between, these are going to be strictly positive or negative always. Okay, so what is, sorry to go on a little tangent there, but plugging in 3 plus 6 is 9. 3 minus 2 is plus times plus is plus, and a plus positive, we're looking for positive, so that's greater than 0, so this is going to be included. So that's our graphical version of the region. So what do we want also? We want the interval notation, so that'll be from negative infinity to negative 6, not inclusive, so we'll put parentheses, and then remember, use this union symbol when you're combining the intervals together, and then 2 to infinity. This is the same thing as saying or, right? This interval or this interval. And then algebraically, we're dealing with x being strictly less than negative 6, or x is greater than 2. Okay, and those are our solution sets. All right, so how about our next example here? We're already comparing this to 0. We don't need to divide out any coefficients. So let's just factor. Okay, so what's the factorization of this? So we want the product to be minus 12. We want the sum to be positive 1. So that should be a 3 and a 4, right? So that will be x plus 4, x minus 3, less than or equal to 0. So what are the roots? So x plus 4 is 0, or x minus 3 is 0. So that means x is minus 4, x is 3. Those are going to be our roots. So on a real number line, are those going to be solid circles or open circles? Well, now we're dealing with less than or equal to, so that means we're going to deal with solid circles, right? So we will fill those in. So negative 4, solid circle, because we're allowing equality now. Solid circle at 3. And now let's pick some test values. So something over here, x is minus 5 should work. X is 0 is always a good candidate if you can pick it, and x is 4. Okay, so if I plug in negative 5 into the factored form, negative 5 plus 4 is negative 1, so that's a negative. Negative 5 minus 3 is a negative. Negative times negative is a positive. And positive is not what we're looking for, right? We want this left-hand side to be we want it to be less than or equal to 0. So we're looking for negatives. We don't have that. Okay, plug in 0. We have 0 plus 4 is positive. And 0 minus 3 is negative. And that is a negative. And that's good. So we're going to include that portion. Right? And then x is 4. 4 plus 4 is positive. 4 minus 3 is positive. And that's going to be a positive. We're not looking for positive, so that's not included. So that's going to be our region. Now that the circles are filled in, the intervals, we're going to be using square brackets. So negative 4 to 3. And the solution will be x's between 4 and 3, but inclusive on those. Okay, now we're going to use the same exact procedure, even if you have something more complicated than a quadratic. If you have a cubic and so on, you just have to figure out how to factor that thing. So looking at this, what do we have? All right, so we have a cubic. Well, for the cubic, the only types of cubics that I'm going to ever give you to factor are the following. It's either going to be sum of two cubes, which we have that factorization form, difference of cubes, which we also have a formula, something that you could factor by grouping, or you have a very clear common factor that can be factored out. And do you see in this case we have x cubed plus 2x squared minus 15x. So do you see that we have a factor of x in all of those? So I can factor out that x, and I'll be left with x squared plus 2x minus 15. So this remaining thing is a quadratic, and then I can factor that. So using my techniques, I want the product to be negative 15, and the sum to be positive 2. So one of them has to be negative, one has to be positive to get a negative 15. But the sum being 2, that means I have to have a positive 5 and a minus 3. So what are the roots then? So we have x is 0. We have x plus 5 equals 0, but then bringing that over, you get x is minus 5. X minus 3 equals 0. Bringing the 3 over gives you x is 3. So these are our roots. Put those on a, you know what, let me actually bring it over here to give some more space, on a real number line. So here's where it's different. We have 3 roots, but the procedure is identical. So plot them in order, though. Just because I have the 0 first, don't put that first, because everything always has to go from, they have to order increasing from left to right. So we'll put the negative 5 first, then the 0, then the 3. Are these going to be filled in circles, or are they going to be open circles? Well, we have less than or equal to. So that means those are going to be solid circles. So we're going to have 3 solid circles for each of those roots. So we're going to have more regions to deal with in this example. So more test points. But what do we have? Negative 5, 0, and 3. Right? Now, what are some test points? So test points. Okay, so pick something up here. X is minus 6. What's in here? X is minus 1. What's in here? X is 1. What's in here? X is 4. Okay, now let's plug each of these into the factored version, right? You could plug them on up here, but it's all we need to do is determine the sign. We're comparing it to 0, and that's how you're going to figure out whether or not to include the region or not, right? That's why they're test values. They're representatives of those regions. So plug in negative 6, you get a negative. Then negative 6 plus 5 is negative 6 plus 5 is negative 1, right? So that's a negative. Negative 6, negative 3 is a negative. Negative times negative is a negative. And is that what we want? We want the left-hand side to be less than or equal to 0. So yes, we're looking for negatives. We already have the zeros, right? Plug in negative 1. What do we have? Negative 1. Negative 1 plus 5 is actually a positive. Negative 1 minus 3 is a negative. Negative times negative is a positive. So we are not going to include that portion. 1 is a positive. 1 plus 5 is a positive. And 1 minus 3 is a negative. And that is a negative. And that's what we're looking for, right? We want the left side to be negative, so we're going to include this portion. X is 4, that's a positive. Then we have a positive, and then a positive. So positive, positive, positive is a positive, not including that. So see the region, a little bit different from what we had before. But there's the graphical solution, this portion and this portion. So writing that as an interval, we have negative infinity to negative 5, and we are including the negative 5. And then we will union that with the interval from 0 to 3, including both the 0 and the 3. And writing that algebraically, we will say that x is less than or equal to negative 5, or x is between 0 and 3, inclusive, right, on all of these things. Okay, so moving on to our next example, we have another cubic, and it doesn't look like we have a common factor of x amongst all of them. So, and this isn't a difference or sum of cubes. So let's try factor by grouping, because if I was going to give you a cubic like this, it would work by factor by grouping. Otherwise, it's just too difficult for you to factor them. So remember, factor by grouping, you're going to take these order in descending order, and then you factor out as much as you can out of the two separated binomials. So I can factor out x squared out of these two, and I will have an x plus 1. And I can factor out minus 25 and get x and then plus 1, still greater than or equal to 0. And then now I have this common factor of x plus 1 that I can factor out. So x plus 1 factored out gives me the x squared and a minus 25. So I have this quadratic that's left over. It's a difference of squares, so that factors very nicely as x plus 5, x minus 5. So then our zeros are x is minus 1, x is minus 5, and x is 5. So we will plot those on a real number line and then pick some test points. Now this is greater than or equal to, so we are going to fill those in with solid circles. Right? So there'll be 3 solid circles. And remember, you have to order these from left to right in increasing order, so negative 5 is the smallest, then negative 1, then our positive 5. And then let's pick some test values. So x is minus 6, x is minus 2, x is 0 is in here, and then x is 6. Okay. So if we plug in negative 6, plug that into the factored form, then you don't have to determine what this is. It's a lot easier. See, this is a really good example to show you that it's much easier to plug into the factored form than actually determining what that is. So negative 6 in here will give us a negative, negative, and then a negative, right? Negative 6 plus 1 is negative, negative 6 plus 5 is negative, negative 6 minus 5 is negative. So negative, negative, negative gives us a negative, but we want something so the left is positive, right? Greater than or equal to 0. We already plotted the 0, so it's going to be either positive or negative. So we don't want this. Plug in negative 2, we get negative, positive, and then negative. So this is negative plus negative. All those multiplication. This will give us a positive. So we will include this, right? So we want that. And then plugging in 0, we get plus, right? Positive, positive, negative. Positive, positive, negative. So that is a negative. We do not want to include that. So plugging in 6, we get plus, 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 which is plus, 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 gives us positive. So we will include that. So that's our graphical solution. As an interval, this would be from negative 5 to negative 1, and then we will union that with 5 to infinity. And to denote the filled-in circles, we're using square brackets there. And then the algebraic solution, negative 5 to negative 1, or x would be greater than or equal to 5.